Welcome to Fall Asleep to Science. In this episode, we will explore modern physics concepts at the university level. This episode will get technical quite quick and assumes you have some knowledge of physics already. Let's begin with relativity. Relativity is the study of how observers in different reference frames measure the same event. There are two types: special relativity, in which observers are in uniform motion or unaccelerated, and general relativity, where observers are in accelerated relative motion. Important to keep in mind when discussing relativity is the invariance of physical laws. First, fundamental laws of physics have the same form in all inertial frames of reference. Next, the speed of light in a vacuum is the same in all inertial frames and is independent of the motion of the source. And finally, simultaneity is not an absolute concept. This means that events that are simultaneous in one frame are not necessarily simultaneous in a second frame moving relative to the first. For relativity, one must be keenly aware of time, or more specifically, time dilation with respect to the proper time. The proper time is the time interval delta t0 between two events that occur in the same space point in a particular frame of reference. If the frame moves with constant velocity u relative to a second frame, then the delta t between the events observed in the second frame is longer than delta t0. In a similar vein, length contraction is also important to be aware of. Proper length is the distance, L0, measured between the points at rest in a particular frame of reference. If this frame moves with constant velocity u relative to a second frame, and the distances are measured parallel to the motion, the distance L between the points as measured in the second frame is shorter than L0. Also under the umbrella of relativity is the Lorentz transformation. The Lorentz transformation relates the coordinates and the time of an event in an inertial frame S to the coordinates and time of the same event as observed in a second inertial frame S', moving at velocity u relative to the first. Then there is the Doppler effect for electromagnetic waves. Recall that the Doppler effect is the frequency shift in light from a source due to the relative motion of source and observer. Then, for a source moving towards the observer with a speed u, use the equation relating the received frequency f in terms of the emitted frequency f0. Some other variables that are useful to know for modern physics are the representations of a particle of rest mass with lowercase letter m moving with velocity with lowercase v, relativistic momentum with lowercase p, and relativistic kinetic energy as capital K. Total energy is given as the sum of kinetic energy and the rest energy through the expression mc². Total energy can also be expressed in terms of the magnitude of momentum and rest mass. Critical to modern physics discussions are photons. Photons are electromagnetic radiation that behaves as both waves and particles. The energy in an electromagnetic wave is carried in units of photons, where the energy of one photon is proportional to the wave frequency f and Planck's constant, but inversely proportional to the wavelength. The momentum of a photon has a magnitude E over c, which is the energy divided by the speed of light. A surface can eject an electron by absorbing a photon whose energy hf is greater than or equal to the work function of the material. This phenomenon is known as the photoelectric effect. This is most commonly observed when photoelectrons are ejected from metal surfaces after incident monochromatic radiation hits its surface. The stopping potential V0 for this effect is the voltage required to stop a current of ejected electrons from reaching an anode. Characteristics of the photoelectric effect are that it is instantaneous, occurs only when the radiation is above a cutoff frequency, and kinetic energies of the photoelectrons at the surface do not depend on the intensity of the radiation. Interestingly, the photoelectric effect can be explained by classical theory. If we assume that the radiation consists of photons that each carry a quantum of energy, then the energy depends only on its frequency, the frequency of the radiation. At the metal surface, the entire energy of a photon is transferred to one photoelectron. Therefore, the maximum kinetic energy of a photoelectron at the metal surface is the difference between the energy of the incident photon and the work function of the metal material. The work function is specific to each metal as it represents the binding energy of electrons to the metal surface. There also exists another effect, known as the Compton effect. This effect happens when X-rays scattered off some materials have different wavelengths than that of the incident X-rays. The incident radiation consists of photons that collide with the weakly bound electrons in the target material. In this case, both the electrons and photons are treated as relativistic particles, and energy and momentum are conserved. The collision that occurs causes inelastic scattering, producing scattered radiation that has a longer wavelength than that of incident radiation. Next topic is Bohr's model of the hydrogen atom. This model has three important statements. 1. An electron moves around the nucleus in a circular orbit. 2. An electron's angular momentum in the orbit is quantized. And 3. The change in an electron's energy as it makes a quantum jump from one orbit to another is always accompanied by the emission or absorption of a photon. Bohr's model of the hydrogen atom explains emission and absorption spectra of atomic hydrogen and hydrogen-like ions with low atomic numbers. It is why quantum numbers are used to describe atomic states and to postulate the quantization of electron orbits in the atom. Next, we have the concept known as de Broglie's matter waves. Any particle of matter that has linear momentum is also a wave. The wavelength of a matter wave associated with a particle is inversely proportional to the magnitude of the particle's linear momentum, and the speed of the matter wave is the speed of the particle. There are measurements for both waves and particles, so it should not be surprising to you that electrons possess a wave-particle duality. There is no classical explanation for this, but double-slit experiments with electrons demonstrate electron diffraction images that are formed because of the wave nature of electrons. This is where quantum theory comes in to put forth the idea of wave packets for electrons. Also included in quantum theory is the Heisenberg uncertainty principle, which states that the wave nature of particles imposes a limitation on the simultaneous measurement of the particle's position and momentum. Now comes the issue of actual photon production. This is where black body radiation comes in. All bodies radiate energy, but the amount depends on the temperature of the body. Wien's law states that the hotter the body, the shorter the wavelength corresponding to the emission peak in the radiation curve is. Then, Stefan's law says that the total power of radiation emitted across the entire spectrum of wavelengths at a given temperature is proportional to the fourth power of the Kelvin temperature of the radiating body. The more classical approach is to look at the absorption and emission of radiation. We find that the exchange of energy between radiation and cavity walls is continuous, but this is not necessarily helpful as it does not explain the blackbody radiation curve. Then, Planck hypothesized that the exchange of energy between radiation and cavity walls takes place only in discrete quanta of energy. This idea gave way to Planck's radiation law, which both agrees with the experimental blackbody radiation curve and explained Wien's and Stefan's laws. That leads us nicely into quantum mechanics. In quantum mechanics, the state of a physical system is represented by a wave function. The wave function is such that its square represents the probability density of finding the particle around a specific location in space. A couple things to know is that wave functions must first be normalized before using them to make predictions, and the expectation value is the average value of a quantity that requires a wave function and an integration. Recall our earlier discussion on the Heisenberg uncertainty principle. We said that it is difficult to measure both a particle's position and its momentum at the same time. Indeed, it is actually impossible to simultaneously measure the x components of position and of momentum of a particle with a high precision. There will always be some amount of uncertainty in the measurements, and as such, the product of the experimental uncertainties for the position and momentum components is always larger than or equal to h bar over 2 due to the wave-like nature of matter. The Heisenberg uncertainty principle also extends out to include uncertainty in energy and time, meaning a quantum state that exists only for a short time cannot have a definite energy. The Schrödinger equation is a very famous equation in physics, as it is the fundamental equation of wave quantum mechanics. It is considered fundamental because it predicts wave functions. When a particle moves in a time-independent potential, a solution of the time-dependent Schrödinger equation is a product of a time-independent wave function and a time modulation factor. The Schrödinger equation can be applied to many physical situations, including scenarios such as the particle in a box and harmonic oscillators. When it comes to a quantum particle in a box, the energy states of the quantum particle are found by solving the time-independent Schrödinger equation. To do this, it is required that the wave function terminate at the box wall. The energy states of a particle in a box are quantized and indexed by principal quantum numbers. When the quantum particle is in a highly excited state, such as near the limit of high quantum numbers, the quantum description of a particle in a box coincides with the classical description. The quantum harmonic oscillator is a different model built as an analogy to the model of a classic harmonic oscillator. The quantum harmonic oscillator models the behavior of many physical systems, such as molecular vibrations or wave packets in quantum optics. The allowed energies of a quantum oscillator are discrete and evenly spaced, where the energy spacing is equal to Planck's energy quantum. For the quantum harmonic oscillator, ground state energy is larger than zero and never at rest, even at the bottom of a potential well. That ground state energy also undergoes quantum fluctuations. Within this oscillator are stationary states, states of definite energy, that have non-zero values also in regions beyond classical turning points. When in the ground state, a quantum oscillator is most likely to be found around the position for the minimum of the potential well. For high quantum numbers, the motion of a quantum oscillator becomes more similar to the motion of a classical oscillator. Finally, we come to quantum tunneling. Quantum tunneling is the phenomenon where a quantum particle that is incident on a potential barrier of finite width and height may cross the barrier and appear on the other side of the barrier. The following are a few possibilities to consider. Assume the energy of an incident particle and solve the stationary Schrödinger equation to find wave functions inside and outside the barrier. The tunneling probability is a ratio of squared amplitudes of the wave past the barrier to the incident wave, and tunneling probability depends on the width of the barrier and on the energy of the incident particle relative to the height of the barrier. In this possibility, the tunneling probability is strongly affected by the barrier width in a nonlinear exponential way. Any small change in the barrier width will cause a disproportionately large change in the transmission probability. Furthermore, as an interesting fact, quantum tunneling is what governs radioactive nuclear decays, which we will discuss later. Modern physics is also concerned with atomic structure, so let's move into a discussion about the hydrogen atom. The hydrogen atom can be described in terms of its wave function, probability density, total energy, and orbital momentum. A neutral hydrogen atom will have one electron, the state of which is specified by quantum numbers. There are 4 quantum numbers by which the state of an electron can be expressed: the principal quantum number n, the angular quantum number L, the magnetic quantum number m sub L, and the electronic spin quantum number m sub s, which is equal to 1/2 in either the spin up, positive, or spin down, negative direction. The Pauli exclusion principle states that no 2 electrons in an atom can have all the same quantum numbers. A hydrogen atom has magnetic properties because the motion of the electron acts as a current loop. Energy levels of a hydrogen atom associated with orbital angular momentum are split by an external magnetic field because the orbital angular moment interacts with the field. The quantum number of an electron can then be used to calculate the magnitude and direction of the orbital magnetic dipole moment of the atom. Interestingly, one could analyze the periodic table to find its structure is explained in terms of total energy, orbital angular momentum, and spin of electrons in an atom. Furthermore, the state of an atom can be expressed by its electron configuration, which describes the shells and subshells that are filled in the atom. When it comes to atomic spectra and X-rays, know that radiation is absorbed and emitted by atomic energy level transitions. As a result, quantum numbers can be used to estimate the energy, frequency, and wavelength of photons produced by atomic transitions. Atomic fluorescence occurs when an electron in an atom is excited several steps above the ground state by the absorption of a high-energy UV photon. X-ray photons are produced when a vacancy in an inner shell of an atom is filled by an electron from the outer shell of the atom, or in other words, the electron in an outer shell degenerates or loses energy to move to a lower orbital. The energy lost is emitted in the form of X-ray photons. The frequency of that X-ray radiation will be related to the atomic number Z of an atom. When it comes to lasers, these are coherent, meaning monochromatic and phase-linked waves of energy. Laser light is produced by population inversion and subsequent de-excitation of electrons in a material that is either solid, liquid, or gaseous. Switching gears a bit again, we now move into the condensed matter physics portion of modern physics. The first thing to know is that molecules form by two main types of bonds. These bonds can either be ionic or molecular. An ionic bond transfers an electron from one atom to another, while the covalent bond shares the electrons. Unlike the ionic bond, a covalent bond involves space-symmetric wave functions. Atoms use a linear combination of wave functions to bond with other molecules. This is referred to as hybridization. Energy changes that occur during bonding are associated with ionic bonding because they depend on the ionization of an electron from one atom, the acceptance of the electron by the second atom, and the Coulomb attraction of the resulting ions. In a covalent bond, these interactions just cancel each other out because of the equal magnitude in opposite directions. Next, molecules possess vibrational and rotational energy. The energy differences between adjacent vibrational energy levels are larger than those between rotational energy levels. These differences are cataloged in the molecular spectra. Furthermore, the separation between peaks in an absorption spectrum will oftentimes be observed. Know that the separation of peaks is inversely related to the moment of inertia of the molecule. It is possible for transitions to occur between the different energy levels, but any transitions between vibrational and rotational energy levels must follow prescribed selection rules. Different materials have different structures due to their chemical components. For example, the bonding in crystalline solids is very different to that of metals. This leads to unique properties and behaviors of such materials. Crystalline solids are materials such as common ionic salts. The packing structures of these salts are found to be face-centered cubics or body-centered cubics. The density of crystal is inversely related to the equilibrium constant, so the densities and equilibrium radii for face-centered common salts are found to be nearly the same. On a final note about the bonding in crystalline solids, know that the dissociation energy of a salt is large when the equilibrium separation distance is small. Metals, by contrast, are not crystalline solids. Instead, they have a free electron model that allows them to conduct electricity, because the electricity is composed of a large number of randomly colliding and approximately free electrons. Though the electrons are free, their allowed energy states are quantized. That quantization appears in the form of very large electron energies, even at temperatures as low as 0 Kelvin. The allowed energies of free electrons in a metal depend on electron mass and on the electron number density of the metal, while the density states of an electron in a metal increases with energy. Perhaps unsurprisingly, there are more ways for an electron to fill a high energy state than a low energy state. As already mentioned, Pauli's exclusion principle states that only two electrons can occupy the same energy level. In filling these energy levels, from highest to lowest at a temperature equal to 0 Kelvin, the last and largest energy to be occupied is called the Fermi energy. Relevant for all solid materials is the band theory of solids. This theory states that the energy levels of an electron in a crystal can be determined by solving Schrödinger's equation for a periodic potential, and by studying changes to the electron energy structure as atoms are pushed together from a distance. We find that the energy structure of a crystal is characterized by continuous energy bands and energy gaps. The ability of a solid to conduct electricity relies on the energy structure of the solid, which is why most metals are very capable conductors. When it comes to semiconductors, The energy structure can be altered by substituting one type of atom with another in a process called doping. There are two types of doping, N-type and P-type. Semiconductor N-type doping creates and fills new energy levels just below the conduction band, while semiconductor P-type doping creates new energy levels just above the valence band. Devices used for doping include diodes and transistors. The diode is an NP junction that allows current to move in just one direction. In the forward-based configuration, the current will increase exponentially with the voltage. The transistor is an NPN junction and is an electric valve that controls the current in a circuit. Transistors are critical components in audio amplifiers, computers, and other electronic devices. Next, we have superconductivity, which is characterized by the conduction of electrons with zero electrical resistance and the repulsion of magnetic field lines. A minimum temperature is required for superconductivity to occur, while a strong magnetic field destroys superconductivity. If you know what Cooper pairs are, know that they can be used to explain superconductivity. Let's move on now to nuclear physics. First, some properties of nuclei. The atomic radius is composed of protons and neutrons. The number of protons equals the atomic number, capital Z. The number of neutrons is the neutron number, capital N. The number of nucleons is the mass number, capital A. Atomic nuclei with the same atomic number but different neutron numbers are isotopes of the same element. And the atomic mass of an element is the weighted average of the masses of its isotopes. Now for nuclear binding energy. The mass defect of a nucleus is the difference between the total mass of a nucleus and the sum of the masses of all of its constituent nucleons. Binding energy is equal to the amount of energy released in forming the nucleus, or the mass defect multiplied by the speed of light squared, and nuclear binding energy is analogous to the ionization of an electron in an atom. When it comes to radioactive decay, there exists a decay constant which can indicate the size of the atom's half-life. If the decay constant is large, the half-life is small, and vice versa. Radioactive decay also obeys a law which uses the properties of radioactive substances to estimate the age of a substance. For example, radioactive carbon has the same chemistry as stable carbon, so it mixes into the ecosphere and eventually becomes part of every living organism. By comparing the abundance of C14 in an artifact with the normal abundance in living tissue, it is possible to determine the artifact's age. You may have already heard of this process, as it is commonly called carbon dating and is popular in the paleontology and archaeology fields. There are three types of nuclear radiation. The first is alpha, in which an atom, represented by capital letter X, decays into X with atomic number Z minus 2 and mass number A minus 4. The lost protons and neutrons produce a helium atom with 2 protons and a total of 4 nucleons. Then there is beta nuclear radiation, where either an electron beta negative or a positron beta positive is emitted by a nucleus. Finally, we have gamma decay, which is where atom X star with atomic number Z and mass number A decays to atom X with atomic number Z and mass number A, producing gamma radiation in the process. Note that when a heavier nucleus decays to a lighter one, the lighter daughter nucleus can become the parent nucleus for the next decay, and so on, producing a decay series. Next to be discussed is fission. Nuclear fission is a process in which the sum of the masses of the product nuclei are less than the masses of the reactants. Energy changes in a nuclear fission reaction can be understood in terms of the binding energy per nucleon curve. Also, the production of new or different isotopes by nuclear transformation is called breeding. Separate to fission is nuclear fusion. Nuclear fusion is a reaction in which 2 nuclei are combined to form a larger nucleus. In this process, energy is released when light nuclei are fused to form medium mass nuclei. The amount of energy released is known as the Q value. Nuclear fusion explains the reaction between deuterium and tritium that produces a fusion, or a hydrogen, bomb, and also explains the production of energy in the sun. Nuclear fusion is the process of nucleosynthesis and is the reason for the creation of the heavy elements. To reiterate, stars are understood to be the location of nucleosynthesis, converting lighter elements into the heavier elements also found in the universe. While nuclear fusion is occurring in stars, they emit measurable energy. This leads nicely into the discussion on particle physics and cosmology. For particle physics, it is important to know that the four fundamental forces in nature are strong nuclear forces, electromagnetic forces, weak nuclear forces, and gravitational forces. Under the umbrella of strong nuclear forces are quarks and short-range forces, while electromagnetic forces include leptons, long-range forces, and quarks. In the weak nuclear forces category are leptons, quarks, and short-range forces. Then in the gravitational category are quarks and leptons. Notice how quarks interact via the strong force, while leptons do not. Quarks and leptons belong to particle families composed of 3 members each. Those family members share properties such as charge, spin, and the participation in forces, but they do not share mass. There also exist elementary particles more fundamental than nucleons in an atom. These elementary particles are fermions, which have integral spin and obey the exclusion principle, and bosons, which also have integral spin but do not obey the exclusion principle. Bosons are the force carriers of particle interactions. Note also that all particles have antiparticles, with which they share the same properties but carry opposite charges. There are 6 known quarks, which are the up, down, charm, strange, top, and bottom. Evidence of quarks is found in scattering experiments, and it is known that quarks cannot exist in isolation due to the strong force. Quarks are considered fermions with half-integral spin and fractional charge. It takes 3 quarks to build a baryon, and mesons consist of a quark-antiquark pair. Many types of particle accelerators have been developed to study particles and their interactions. Such devices include linear accelerators, cyclotrons, synchrotrons, colliding beams, and multipurpose accelerators. Colliding beams are used to create massive particles that decay quickly to lighter particles, and multipurpose accelerators are used to design all aspects of a high-energy collision. In these particle accelerators, charged particles are measured by using a magnetic field to bend the particles in a circle. Calorimeters then absorb the particles for further measurement. Elementary particle interactions are governed by particle conservation laws, which can be used to determine what particle reactions and decays are possible. Such particle conservation laws include the baryon number conservation law and the 3-lepton number conversion law. Both laws are valid for all physical processes. There is also the conservation of strangeness, but this is valid only for strong nuclear interactions and electromagnetic interactions. A model known as the Standard Model describes the interaction between particles through the strong nuclear, electromagnetic, and weak nuclear forces. In this model, particle interactions are represented by the Feynman diagram, which is a space-time graph. With the Standard Model, electromagnetic forces are described to act over a long range, while strong and weak forces act over a short range. These forces are transmitted between particles by sending and receiving bosons. From a cosmological perspective, the universe is expanding like a balloon, and has been since the Big Bang. This means that every point is receding from every other point. Distant galaxies are moving away at a velocity proportional to its distance away from us, at a rate of 70 kilometers per second per megaparsec, for example. The farther a galaxy is from us, the greater their speed. Following this observation, we can conclude that the universe must be 13.7 billion years old. We know of the Big Bang because of all the cosmic background radiation that is present in the universe. Such background radiation would only be possible if such an energetic explosion occurred. We know that the early universe was hot, dense, isotropic, and expanding, but a vast portion of the mass and energy of the universe is still not well understood. With that, we conclude this episode of Modern Physics at the undergraduate level. We touched on everything from relativity to photons, quantum mechanics and atomic structure, condensed matter physics, nuclear physics, and particle physics and cosmology. If you enjoyed this episode, be sure to check out the others on this channel. Leave a comment, like, and subscribe to help more people find this podcast. Thank you for listening.